All right, we're all here. Let's see, we were talking about asymptotes, graphing functions that have asymptotes, taking limits to infinity, and so on. So let's see what I was going to tell you about that. Do you have questions? Let me get started. You're back on section 4.4. Limits to infinity help us find horizontal asymptotes. And limits that become infinite help us describe what's going near a vertical asymptote. Oh, let me see if that's visible. Let's go up, up. Go up. I have to push my camera. Oh, there we go. I went up. Okay. That's just where to go. Right there. Okay, so one of the things that we were doing when we were looking at limits to infinity is using the fact that as x gets big, one over x to a power is going to go to 0. So when we were taking limits to infinity on rational expressions, one of the steps that I showed you was that you can divide every single term in that rational expression by the highest power on the x that you see. That'll leave you some terms that look like that in the expression. And then when x gets big, you can wipe those out and say that those go to 0. What's left is your limit. For instance, we're taking the limit as x goes to infinity, and we have x squared plus 4x minus 1 on top, and 2x squared plus 1 on the bottom. If we employ that idea where we multiply top and bottom by 1, in the form of whatever the highest power of x is, like here it's x squared. So if I multiply top and bottom by 1 over x squared, then I am in essence dividing everything by x squared. Okay, so x squared is the highest power. So that's what we're going to do next. We're going to rewrite the expression by dividing everything by x squared. I'm going to do that part in my head, cancel as we go. So this limit looks like, I'll have an x squared divided by x squared, which would leave me a 1. 4x divided by x squared simplifies to 4 over x. And then I have a minus 1 over x squared. On the bottom, we'll have a 2 plus a 1 over x squared. So this is an equivalent expression when x is away from 0, and we're going to infinity, so x is really away from 0. So we're okay in doing that step. Black markers aren't working for me. But that leaves terms that we said are going to go to 0 as x goes to infinity. So we take the limit term by term, all the way, top and bottom. And anywhere we see something that looks like that, x is going to infinity. So 1 over x to a power is going to go to 0. Same thing here. So I got a bunch of zeros added to the 1 and the 2, and that leaves us just a limit of 1/2. Then as we were leaving, I said, that's going to happen every time that you have the highest power of x the same as the highest power of x in the denominator. Right here is where that 1/2 comes from. That's going to happen every single time when you're taking limits to infinity. If you have same at the highest degree on the top as the highest degree is on the bottom, this dividing step just results in the ratio of the coefficients. So note, first thing is, if the degree on the top is equal to the degree on the bottom, then this limit to infinity will always, always, always yield the ratio of the coefficients of the highest power of x. Always. So we don't have to do that dividing step. We'll always recognize that. Now let's put the highest power of x on the bottom and see what happens to those cases. Let's look at the limit as x goes to infinity. Let's see where I can move. Out here. Let's look at the square root of x plus 4 divided by 3x minus 2. Square root of x plus 4 divided by 3x minus 2. In this case, the highest power of x is x to the first power. So if I want to develop terms that look like fractional terms, I'm going to divide everything by that x to the first power. So when I take the square root of x and divide it by x, remember that a square root is a 1/2 power. And when we divide, we subtract exponents. So I take that 1 that's the exponent on the bottom, subtract the 1/2 power, and I get a 1/2 power in the denominator of this one term. So we can rewrite that as the limit as x goes to infinity of 1 over x to the 1/2. I'm dividing by x here, so I get plus 4 over x. This one simplifies to 3, and that's minus a 2 over x. Now we use our observation that as x gets large, 1 over x to any power is going to go to 0. And that wipes out 3 of my 4 terms. My numerator then adds to 0. My denominator adds to 3. So our limit is just whatever 0 over 3 is, and duh, even on Friday, that's a 0. That same pattern happens whenever the degree on top is smaller than the degree on the bottom. In the long run, the bottom grows faster than the top, so the fraction goes to 0. So if the degree on the top is smaller than the degree on the bottom, the limit to infinity is always 0. Excuse me. Oh, I'm not wearing a mask. Why didn't you tell me that? Don't get out of this mask business. Except for next year's Texas game, I have to put my mask on so nobody can see what I'm yelling at the crowd in unison.
I can only imagine.
Well, you guys weren't here when Baker Mayfield went to Oklahoma and started Mountain Tech. And the whole game, it was F.U. Baker, F.U. Baker, without the spelling of it. So Beard is going to get that. I think children under 18 are not going to be allowed into the game. If the degree on top is smaller than the degree on the bottom, the limit to infinity is always 0. So I call this one the bottom heavy case. If the fraction is bottom heavy in terms of the power, then the limit is going to go to 0. Over here. If it's upside down, just put the higher power, flip this fraction upside down. And then the 3 would be on the top and we'd have a bunch of zeros on the bottom. But if you take a fixed number and divide it by things that get close to 0, then that fraction becomes infinitely large. So if the degree on the bottom is smaller than the degree on the top, or I'm going to write if the degree on the top is bigger than the degree on the bottom, or a top-heavy fraction, the limit is infinite. The limit to infinity is infinite. Either it goes to plus infinity or minus infinity. What these limits describe geometrically is what the graph does at the tail ends of it for large values of x or for small values of x. If we have some sort of limit, then both ends will kind of go toward that y value. Sometimes only one end does, but the ends will go toward that y value. If the limit is 0, then that y value is the x-axis. If there's no limit, then our graph will look kind of like a polynomial where the ends take off maybe both in opposite directions or both together. So, and this is the case that's top heavy. The top heavy fraction goes to infinity. The bottom heavy fraction goes to 0. But now we have to look at the cases where the expression isn't x to a power, where we've got our other trig functions or our other transcendental functions involved. The limit as x goes to infinity of e to the negative x times the cosine of x. So we don't even have a fraction, but the fact that we have an e to the negative x means we can make that a fraction. I can write that as the cosine of x over e to the x, and I will. All right, so no matter what the x is, big or small or medium size, cosine of x is here. 1, -1, and numbers in between. So we're taking those numbers and we're dividing them by e to a power. Well, e to a big power is really big. So take numbers between 1 and -1 and divide them by a really, really big number. What's going to happen? This numerator is going to be some number between 1 and -1. And this is going to be something that's really, really, really big. So be what? Bottom heavy, which means the limit is going to be 0. All right, now the numbers could possibly be confusing to you. So let's look at the limit as x goes to infinity, say of x raised to the 1.4 power minus 1. And down here, x is raised to the square root of 2 power plus 1. So essentially my question is, which is bigger? 1.4 or the square root of 2, or are they the same? Oops, I can move that over. Oh, good. Audrey, which one's bigger? They're not exactly the same. Because when you punch in square root of 2, you get 1.4, blah, 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 right? This is a non-terminating, non-repeating decimal. This is a terminating decimal. So even though it's 1.4 to the 10th place, but if I go to the hundredths, thousandths, and so on, there's more there. So the square root of 2, even if it's slightly bigger than 1.4, it is bigger than 1.4. So when x is big enough, the bottom is going to overtake the top, and the limit is going to be 0. Okay, doesn't have to be greatly larger, any size larger. Okay, so last time we looked at the limits that become infinite. So let's look at these two limits. The limit as x goes to 0 from the left and from the right of 4 minus x over x. Let's do from the left and from the right. And the magical thing about the 0 is that it gives me 0 in the denominator, but not in the numerator. So here I'm dividing 4 minus x by numbers like a negative 0.1 or negative 0.01 or negative 0.0001. And here I'm dividing them by numbers that are real close to 0 but positive. What did we do to decide on what these limits were? They are infinite, because I'm taking essentially a constant and dividing by 0, or a number close enough to 0. I have to decide whether their y values are going to plus infinity or to minus infinity. You can plot points, or you can take the derivative and look at the slope. And that's what I'm going to do. I'm going to take the derivative. Maybe I'm going to take the derivative by writing this as 4 over x minus 1, because it's real easy to take the derivative of that. I just broke it up into 2 fractions. So if f of x is equal to 4 over x minus 1, then f prime of x is -4 over x squared. Right? X to the -1, bring it upstairs, bring the power down, raise it to 1 power less. And here's what this is telling me. No matter what sign x has, it's going to be positive after I square it. Then I'm going to take that and divide it into a -4. So I'm taking numbers that are tiny, close to 0, and I'm squaring them, which makes them tinier, and then positive, and I'm dividing these real small numbers into 4. They're both going to be big negative numbers, aren't they? Both of these limits go to -infinity. Now I want to put our knowledge of horizontal and vertical asymptotes together to sketch graphs. Let's start with this function. Let's graph this. So the first thing to note is that when I take the derivative, I don't get any critical numbers. Right? There are no values of x that make the numerator 0. I do have a vertical asymptote at x is 0. And I found that around that vertical asymptote, the sign of f prime is always negative. So the graph decreases and decreases. Right? I'm graphing this thing right here that we just did. Now I want you to tell me if there's any horizontal asymptotes. Any? Whether you look at it in this form or in this form. It's the behavior of that fraction as x goes to infinity. Anybody? Same power. Not gonna play along today. The degree on top is equal to the degree on the bottom. The limit to infinity is always the ratio of the coefficients. -1 over 1. So the line y is equal to -1 is the horizontal asymptote. This says we have no max or mins. We have a strictly decreasing graph. And then at the ends of the graph, the ends hug the line y is -1. So here's y is -1. Here's x is 0. It's never going to hit either one of those dotted lines. When I am to the left of 0, the graph has to decrease and approach this line on the end. So it can't be up in this little quadrant here. It has to be down in this quadrant there. And it has to bend so that it decreases here and decreases from y is -1. Right? Then on the other side of that asymptote, it has to decrease again. So it can't be here because we know that this end has to go toward that line. It has to be up here. And it has to bend concave upward so it hugs that asymptote and the other asymptote. So there are no max and mins, and the ends hug the lines the way we say. Do they? Yeah, that's decreasing. No max or mins. Yep. That's what's going on there. In fact, this point where it crosses the x-axis is where the numerator over here is equal to 0. 4 minus x is 0, then x is equal to 4. So that was a clue that it was going to be above the x-axis. Okay? So that's where we're going to use our limits that become infinite and our limits to infinity to help us graph things that may or may not have max and mins. So the next one's a big one, graphing functions that have asymptotes. This one, the next one I have here is x squared over 1 minus x squared. We're going to identify the asymptotes, identify relative max and mins, and if we need to, determine where it's concave up and down. So let's take the following steps to graph this thing. Let's identify any horizontal asymptotes. It's a horizontal line, so we write it as the equation of the line y is equal to. Identify any vertical asymptotes. Those are vertical lines, so they have the equation x is equal to. The horizontal asymptote is what we get when we take the limit to infinity. And now you can eyeball that limit. What's that limit going to be? 1. Y is equal to 1. No horizontal asymptote. Vertical asymptotes occur where there's not a y value. There's no y value where the denominator is 0 and the numerator is not 0. So there's 2 vertical asymptotes. What 2 values of x make this 0? Let me stand up here until the blood comes out of my arm. X is 1 and x is -1. Now let's look for all the stuff that the first derivative tells us. Let's take the first derivative and see if we know if this thing has any relative max or mins and where it's increasing or decreasing. Let's take the first derivative. Let's see what we find. So we're going to do some quotient rule action. At the bottom times the derivative of the top. That's just going to be a 2x. Minus the top times the derivative of the bottom. X squared times the bottom is just 2x again, all over the bottom squared. When I multiply that out, this will look like 2x cubed minus 2x minus 2x cubed over x minus 1, x squared minus 1 squared. So we just get a 2x on top, a minus 2x at that. And so our derivative is 0 only when the top of this fraction is equal to 0. And so we get a critical point at x is 0. Now we got to cut up the number line and look at the sign of the derivative around the critical number. But it's also possible that the derivative could change sign around the asymptotes. So we're going to use the asymptotes, the vertical ones, as cut points on the number line as well. So here's my derivative. I want the sign of the derivative. My two asymptotes are at -1, 0, and then 1. And in each of those intervals, we want the sign of f prime. I'll emphasize that these are asymptotes by drawing them dotted. And we're plugging things into that derivative that I have to the left of the number line. So let's put in a -2. If x is -2, my numerator is positive. If this x is -2, it doesn't matter because my denominator is squared. So the bottom's always positive. I said the top was going to be positive. So the whole fraction over here is positive. Now I'm going to think about a number between -1 and 0, like -1/2. I put a -1/2 in here, and that's positive. Denominator is positive, so the whole thing's positive. Now I'm going to put a +1/2 in for x. Again, the bottom's positive. The top, though, is going to be negative this time. And the same deal over here. So the graph is going to increase to the left of the asymptote, keep increasing, then decrease, and then keep decreasing. Increases to the left of -1, and then between -1 and 0. Decreases to the right of 0, but you can't include 1, so we'll break it up around the 1. Our critical number was at x is 0. Is it a relative extreme value? Which one is it, a max or a min? It is a max, comes up and then down around that 0. We don't have a relative min. That's probably enough to get the graph. We probably don't need to check the concavity. Let's see if we can make it look like what we say. Let's see, when I plot f of 0, I get 0. We get a 0 on top of here. So it goes to the origin. The origin is going to be our max. Then we have those asymptotes at -1 and 1. In between the asymptotes, it looks like that, kind of like a parabola. That's what the x squared is doing for us on the top. Guess what this would look like between the asymptotes if I had an x cubed on top here? It would look like an x cubed graph in there. If I could have an x squared graph in there, does that to it. That's what that's saying. Now what this says, oh, did we have a horizontal asymptote? I didn't put that in yet. Let's put that in at y is equal to 1. What that y is equal to 1 and x is equal to -1 does is it gives me two quadrants over here, or two sectors of this plane. The graph is either up here and stays up here, or it's down here and stays down there. It has to be strictly increasing. So here's strictly increasing. It can't be down here. It won't be approaching that asymptote. It has to be up here. So you draw your little hyperbola up there. Okay, same deal over here. Here's that asymptote. I know the ends of the graph are going to approach here. Whether they're this way or that way, we're going to figure it out. This says the graph has to be decreasing. The only way for the graph to decrease and have ends that approach that asymptote is if it's up here, not down here. So it's got to be up here and bending like a hyperbola up there. You see my rationale there? Okay, this says it's decreasing. And this says the end of the graph, which would be my elbow, has to go toward the line y is equal to 1. So I had two choices, up here or down here. But if it's decreasing down here, my elbow is not going toward y is equal to 1. It has to be up here. Mask. This mask is itchy. Try this next one. Okay, I got a second one for you. The next one we're going to graph by identifying asymptotes, relative max and mins increasing, decreasing. The same for f of x is equal to x squared minus x minus 2 divided by x minus 3. So let's ask ourselves the same questions. Are there any horizontal asymptotes? Are there any vertical asymptotes? Horizontal asymptote comes from taking the limit as x goes to infinity. What happens to an expression where the bigger power is on top than it is on the bottom? The ends go up or down, right? There's no horizontal asymptotes because it's top heavy. There's a vertical asymptote. There's a place that makes the bottom equal to 0. X is equal to 3. You got to make sure the top is not 0 and x is 3. So let's make a quick check. 3 squared is 9. Minus 3 minus 2 is not 0. So that is a vertical asymptote. Now I guess we're going to take the derivative. Do the quotient rule. Let's see how much that simplifies. Scoot my camera over. Maybe. Wrong way. That away. We're going to do the quotient rule right up there. Bottom times the derivative of the top, which will be 2x minus 1 minus the top, x squared minus x minus 2 times the derivative of the bottom is just 1 over the bottom squared. We need to simplify the top because it's where the top of this fraction is 0 that there are possible critical numbers. So let me boil out this first batch. First, I'm going to multiply those two terms by x. Then I get 2x squared minus x. Now I'm going to send a negative 3 through there. Then I get a negative 6x plus 3. This one doesn't do anything for me. Let's distribute the minus sign. So I have minus x squared plus x plus 2. And now we simplify. I'm going to have a 1x squared. And then I have minus x minus 6x is a minus 7x. Now we're back to minus 6x. And then 3 plus 2 gives me plus 5. So I think we have two critical points because I've got a second degree polynomial on top. The derivative is 0 when the numerator is 0. We got any factors of positive 5 with the same sign that add to negative 6? Minus 5, minus 1. So our two critical numbers are x is 5 and x is 1. So we're going to test the sign of the derivative to help us determine where this is increasing or decreasing. So I'm going to put those numbers on the number line right next to the derivative. There's the 1, there's the 5. Uh-oh, I got to put a 3 in here, but I don't want to use that as a test point, and it's very possible that there's a sign change around the asymptote. So put 1, 3, and 5 on your number line. We're going to plug things into the derivative, but we don't have to worry about the bottom because look, it's squared. That's always going to contribute a positive value. The numerator factors like this, so it might be easy to just plug things into each factor and see if they multiply to a positive or negative number. So for instance, if x is 0, either place, they get a positive derivative. If x is 2, I've got a negative times a positive. A negative times a positive is going to be negative here. Let me remind you that I'm finding the sign of a prime. And here I use x as 4. 4 minus 5 is negative. 4 minus 1 is positive. Negative times positive is negative. And then if x is 6, both of those are positive. And so we have the graph that goes up, then down, down, then up. So x is equal to 1 is a relative max. X is equal to 5 is a relative min. So let's write all that in interval notation. We have a relative max at x is 1. We have a relative min at x is 5. It increases to the left of 1, and then again to the right of 5. Decreases on each side of 3. From 1 to 3. And then again from 3 to 5. Now let's plot those two critical numbers so I know where to put them on the XY plane. So we're going to go back over here and plot them. I need f of 5 and f of 1. F of 5 is 25 minus 5 minus 2 all over 2. 20 minus 2 is 18 divided by 2 is 9. So the ordered pair 5, 9 is our relative minimum. F of 1, 1 minus 1 minus 2 over 1 minus 3 is a minus 2 over a minus 2. And so the ordered pair 1, 1 is a relative maximum. Okay, so here we go. Put this in here. Vertical asymptote at x is 3. Boy, that's a straight dotted line, isn't it? Then I've got the ordered pair 5, 9. Let's just put that here. And that one's going to be a min. And then 1, 1 We said one was going to be a max. There's no horizontal asymptote, so the ends of the graph are either going to take off up, take off down, or some mixture. So let's work on this bit here to the left of 3. We're going to rise up, hit the max, fall down. It's like a little parabola here, doesn't it? Rise up, hit the max, fall down. On the other side, we're coming down to the minimum at 5.9 and then turning around, back around to go back up. So a carbon copy is up here, down to hit that, and then back up. One more little interesting tidbit. When the degree on the top is larger than the degree on the bottom, there's something called a slant asymptote. There's a slant asymptote, a diagonal line coming through here that's bounding this end and that end. We find the slant asymptote by long division. When the degree on the top is bigger than the degree on the bottom, there will be a slant asymptote. The slant asymptote will be the equation of a line, y is equal to mx plus b, unless the asymptote is more than just a line, that we find by long division, and it's the quotient part, not the remainder part. It's the quotient part that we get in long division. So I'm going to take x minus 3 and divide it into x squared minus x minus 2. So let's see if you remember long division. But you have to remember it pretty quick because we only have about 2 minutes left. We look here at the x and look at what we need to multiply by to get the first term here. So I'm going to need to multiply by x. So I put it up here above the x column. Then I take that x and multiply both of those terms in the x minus 3, line them up. I'll have an x squared minus 3x. And then we subtract that line from the line above it. And so when I subtract the minus x, I get minus x plus 3x gives me 2x minus 2. So this x divides into the 2x again with a factor of 2. I get 2x minus 6. And then when you subtract, I get a remainder of 4. This guy up here is the slant asymptote. Y is equal to x plus 2. So it's going to appear right here. Oops, it should be up 2 units, should go through 2. So my scale is off a bit, so I just make it crooked lines. Slope of 1, and the ends of the graph then start hugging that line. So this is going to get real close to that line here, and this is going to get real close to that line there. You done stuff like that before? No, not even in college algebra or pre-calculus? Or...
I've heard of this line.
But it doesn't really add much interest to our picture. We pretty much had to graph the thing without it. So it's not that important to know that. It is important to know horizontal asymptotes and vertical asymptotes. I did want to work a couple problems where the graph doesn't have asymptotes, but it has either a sharp corner in it, a cusp, or a vertical tangent line. I guess we'll do that on, not Monday. Monday's another one of our off days, on Wednesday. Do you have enough work to keep you busy till Wednesday? I can always add more. Sure, you're good? You're good? Okay. All right, enjoy your time off, but don't just take time off. Take your calculus with you. I'm logging out unless you got a question for me. Good? Okay, I'm out of here.